Welcome back to the lectures. We will conclude the elementary part of the quantum mechanics of hydrogen atom with this part 5, where I shall give a brief description of radial functions and radial distributions of the hydrogen atom. Now recall that the hydrogen atom wave functions for the Schrodinger equation, that is the solutions, have been earlier represented by psi with 3 quantum numbers n, l and m as a function of the 3 coordinates r, theta and phi, and this was written as r n l of the radial coordinate r and y l m theta phi. This phi or phi, I seem to have mixing these two things, but remember phi or phi in the context, I mean they both mean the same thing for this lecture. The radial function r n l r and the radial distribution that we will consider in this lecture, namely it is r square or n l of r squared, okay, or the probability distribution, the wave function component and the probability distribution for the radial part. Okay. Now we have not talked about the solutions of these earlier, other than briefly mentioning that the radial functions have, with the quantum number n, l and r, have the range for the quantum numbers as n equal to 1, 2, 3 all the way up to infinity, and l is equal to 0, 1, 2 up to n minus 1 for any n. Therefore, when n is 1, we have the radial function which is r1 0 of r, and the solution of the radial Schrodinger equation using the calculus of differential equations, the solutions of differential equation, gives us what are known as log-8 polynomials and the exponentials, and this particular function r1 r is like exponential minus r by a naught, where a naught is the Bohr radius. And 0.59 angstroms. For n equal to 2, we have two solutions, namely l equal to 0 and l equal to 1, and the function for l equal to 0 is 1 minus r by 2 a naught times e to the minus r by 2 a naught. Okay. For l equal to 1, the radial function happens to be r times e to the minus r by 2 a naught. Okay. I have neglected the normalization constants or the prefactors. Constants. But if I don't, if I have to write this exactly, then r1 0 of r is equal to 2 by a naught raised to 3 by 2 e to the minus r by a naught. This normalization constant is obtained by the following procedure, namely the psi star n l m psi n l m d tau, the integral is equal to 1, which when we use the spherical polar coordinates has the following form: r equal to 0 to infinity, the radial function n L of R squared, because this is real, and R square dr, which is the radial part for the d tau. Then you have theta is equal to 0 to pi sin theta d theta integral phi is equal to 0 to 2 pi d phi y L m theta phi, the absolute square, this has to be 1. Now you see that the d tau is essentially r square dr d theta sin theta d phi, and the rest of it is psi star n Lm psi n Lm. Therefore, when you do this integral independently of this the theta phi integral, note that the definition of YLMs are such that this part is 1, and therefore the radial part is given by this 1, and now you can see immediately why the quantity R n L of R square is called the radial probability or radial distribution, because this probability, when it is calculated for all values of R from 0 to infinity, is equal to 1. Therefore, you see the radial probability in the case of the hydrogen atom is not just the R n L squared, but it is multiplied by the R square, and that is important to remember. It is not just the square of the function. Let us look at these functions in the pictorial form. The first one is like exponential minus R by A naught. This is n is 1, L is 0, and this is a straightforward exponential, the radial function, and the integral, the square of this function, if you write the normalization constant also, if you write that, remember it is 2 by A naught to the 3 by 2. Okay. Therefore, if you do that, the integral that you have to worry about for radial probability is R square e to the minus 2 R by A naught, as this is the square of the radial function, and then you have the multiplied by 4 by A naught cube. Okay. So, this is the radial probability, this is the radial function. Okay. The radial function is given like this, and the radial probability, if you have to plot it, if I have to make a brief plot of this, I do not have it in the screen here. If I do the plotting as a function of R, if I do the R square, the radial probability goes like that. It is 0 at or equal to 0. The function, radial function itself is not 0 at or equal to 0, but the radial probability, because of this R square, is always 0 at the nucleus, as the value, the probability density is 0, and the probability distribution is that this is R square, the area of this for all the under this graph is equal to 1. That is a normalization. What about radial function for the hydrogen atom at n equal to 2? There are two values, L equal to 0 and L equal to 1. So, if I have to look at the L equal to 2, the functional form, if you remember I wrote down, is 1 minus R by 2 A naught e to the minus r by 2 a naught. You can see clearly that when r is 0, this is 1. So, you start with some number depending on what the constant in front of is, that is a maximum here. But at r equal to 2 a naught, as r increases from 0 to 2 a naught, you see that the function drops off while the exponential is also minus r by 2 a naught. So, you see that this function goes down, but for all values for all values of r greater than 2 a naught, this will increase because this will increase, but the exponential will decrease. Therefore, after some time the function goes such that the exponential tapers it off. So, this initial increase is due to this. This is the part of what is known as the log-air polynomial, which are solutions for the radial equation. Okay. For L equal to, this is L equal to 0, I am sorry, this is the function for L equal to 0, and for L equal to 1, n equal to 2, the radial function that you have is r e to the minus r by 2 a naught, with again some prefactors, that is the normalization constants. You can see that this function is 0 at r equal to 0. As r increases, this increases, but this decreases. So, there is a competition between the increasing r up to a point there is a maximum, and then the function is reducing due to the exponential. Even though r is increasing, the exponential dominates, and therefore the function goes to 0 for large values of r. This is the radial function for n equal to 2, L equal to 1, and the radial distribution is r square multiplied by square of this function, which is again another r square, and e to the minus r by a naught. This is the radial distribution. This is r 2 1 radial function square multiplied by r square. So, again the maximum that happens is quite far away from the 0. N is equal to 3 has 3 possible functions, namely L equal to 0, L equal to 1, and L equal to 2. This one is L equal to 0. The form of the radial function is essentially 3 minus r by 2 r by a naught plus 2 r square by a naught squared. This is the quadratic in front of the function multiplied by e to the minus r by 3 a naught, n equal to 3. Okay. The quadratic has 2 solutions, both of which are positive, and you can see that those 2 solutions are these. That is, the quadratic goes to 0 for these 2 values of r. If you factor this out, this quadratic with the 2 roots, these are the 2 roots, and you can see that when r is 0, the function is positive, it is non-zero because of the 3 and the prefactor in front of it, the normalization factor in front of it, it is somewhere here. And then as r increases, if you write this as the 2 roots quadratic, r minus a1 times r minus a2 times e to the minus r by 3 a naught, and if a1 is less than a2, you can see for r less than a1, r is also less than a2, therefore this product is positive and the exponential is always positive but a small number, the function is positive between 0 and the first root. Between the first and the second root, because this product is negative, or is greater than a1 but less than a2, the function is negative, but it is also multiplied by e to the minus r by 3a0. And for r greater than a2, this is positive, so the function tends to increase as r square. However, e to the minus r by 3a0 eventually brings it down to 0. Okay. So it has two roots called nodes. The previous one has one node, n equal to 2, L equal to 0. When n equal to 2, L equal to 1, no nodes. When n is 3, L is 0, there are two nodes. When n is 3 and L is 1, the radial function turns out to be 3 1 of r, turns out to be, barring the normalization constant, it is r times 1 minus r by 6 a naught times e to the minus r by 3 a naught. So you can see that this is 0 when r is 0, and when r is 6 a naught. So between 0 and 6 a naught the function increases, and at r equal to 6 a naught it goes to 0. Okay. And for all values of r greater than 6 a naught, this whole thing is negative, and you can see that the function will decrease r square. Okay. But the exponential of minus r by 3 a naught eventually brings it back to 0. Okay. So here is the maximum, and then the function goes to 0 for, but only one node. And the last one, when you look at n equal to 3, L equal to 2, the function is r square e to the minus r by 3 a naught. This is like the radial function r3 2 of r. I mean, I have not put in the normalization constant, but that is what it is, and the r square has only one maximum, and then the exponential eventually goes to 0, no nodes. Therefore, the log air polynomials which are there for various values of n and L are basically polynomials in the the order of the polynomial, or the degree of the polynomial is n minus L minus 1. That is the number of radial nodes. Because if the polynomial is of this degree, it has that many roots. So you see that when n is 1, L is 0, there are no roots, no nodes. When n is 2, L is 0, that is one node, no node, then 2, 1, 0. When n is 4, you have 3, 2, 0, 1, 0. So the number of nodes are like this. And for angular functions, we saw already for any L has L nodes. So the total number of radial plus angular nodes for any function is n minus L minus 1 plus L, which is n minus 1. These formulas are somewhat familiar to you from the elementary school introduction of the hydrogen atom functions as pictorial functions, but you can see that the radial functions are like this, and the radial probability is the square of the radial function multiplied by r square. So let me conclude by putting all these functions together for each value of n. So, this is for n equal to 2, the two functions are, this is L equal to 0 and L equal to 1, gives you an idea that the larger part or the maximum value of these functions are slightly farther from the maximum values that you would see for n equal to 1. This is a statement that the 2s orbital is more extended than the 1s orbital. The maximum for the 2s orbital or the probabilities for the electron in the 2s orbital are maximum when it is slightly farther away compared to the electron being in the 1s orbital, where the maximum is closer to the Bohr radius. And the same thing happens for n equal to 3, the maximum is even shifted further and there are two nodes. So, if you look at the radial square functions, namely the r square times r3 0, if you square, if you look at that function, the radial probability will look like this quantity here. The radial probability will look somewhat like that, okay, with the two nodes corresponding to the points where this polynomial, the radial function goes to 0. Okay. And then for 3 1 you will have two maxima, and for 3 2 only one maxima, but the maximas are all towards the farther side, meaning that the 3s orbital is much more extended in space than the 2s orbital, than the 1s orbital, and the maximum of the 3s orbital is quite far away compared to that of the 2s orbital, and that is also far away compared to that of the 1s orbital. So, this picture of Bohr having circular orbits drawn, those circles essentially represent something close to a maximum. We have now replaced the circle by a probability distribution through a more exact treatment of Schrodinger. But then the only question that I would not be able to answer, why Schrodinger equation? We do not know the answer. Okay. Let me conclude this lecture with a note on the probability statements, probability distributions. The wave functions psi n l m's are chosen to be normalized wave functions. So, if I put all the three coordinates by the abbreviated symbol tau, then it is psi star n l m psi n l m tau d tau, the integral is equal to 1. This is normalization. From the functions given in the lecture notes for the individual or n l r's and the y l m, the integral now takes the specific representation as a triple integral r equal to 0 to infinity, theta is equal to 0 to pi, and phi is equal to 0 to 2 pi. You have the radial function square, you have the absolute value of the spherical harmonics theta e squared, absolute value, multiplied by the d tau, which is r square sin theta d r d theta d phi. Okay. That is equal to 1, and the orthogonality of these wave functions as being solutions of a Hamiltonian, which is a Hermitian Hamiltonian. I have again introduced a new term called the Hamiltonian as a Hermitian operator, which have real eigenvalues for all the eigenvalues are real. The Hamiltonian operator, the wave functions psi n l m tau, psi star, psi n prime l prime m prime tau d tau, is these functions are orthogonal to each other, and if I have to write that in the integral notation, the answer is the Kronecker delta n prime, Kronecker delta L prime, m prime. This is Kronecker delta, meaning delta ij is 1 if I is equal to j, delta ij is 0 if I is not equal to j. Therefore, if n is not equal to n prime, if L is not equal to n prime, if m is not equal to n prime, any one of them, any pair of them, if they are not equal, the wave function is wave functions are orthogonal, and therefore the wave functions being already normalized are thus known as orthonormal basis functions for all other problems of atoms. If we need to, we can always use the hydrogen atom wave functions as the basis functions, orthonormal basis functions, as representing the wave functions for any other atom or any other system of nuclei and electrons together. We wish to. We will not use that, but these are analytically known, that is analytically represented, and we do not have much more of such analytic representations for other atoms. In fact, for any other atom which has more than one electron, we do not have such analytic solutions. Therefore, the hydrogen atom solutions are extremely important. I have not covered the hydrogen atom here in the form of the actual mathematics and the solution of the differential equation that is usually given in a higher or a slightly more advanced course. But please remember, we were trying to study the functions and represent them and look at their properties with the confidence that these functions have been derived by mathematicians and physicists and have been shown to be exact. Hydrogen atom is an extremely important problem in the understanding of the quantum mechanics of atoms and molecules, and the angular distributions, the radial probabilities, the radial distributions, all these things enhance one's capability in using similar mathematical techniques and tools in the understanding of atoms with many electrons, and the only method that we can use for such studies are known as approximation methods. We do not have exact solutions for the differential equations. We use approximation methods known as perturbation methods or variational methods, but those will form part of another course. And as far as this elementary introduction to hydrogen atom is concerned, until then, thank you very much.